Jnanam paramam dhyayam. Knowledge is supreme.
Let us just recall what we had done in the previous lecture. We have started looking at what is called the rank of a matrix. So, we defined for a matrix A, which is m cross n. Look at its row echelon form. In particular, you can also look at the reduced row echelon form. Then the rank of the matrix is defined as the number of non-zero rows in that matrix or the number of pivots, both are same. So, we had mentioned that if you take row echelon form of a matrix, that may not be unique, but the number r, which is a number of non-zero rows, it is same in all row echelon forms, right. And the first non-zero entry was called pivot. So, number of pivots is also fixed once you have row echelon form. So, the rank is defined to be the number of non-zero rows in the row echelon form or reduced row echelon form. So, clearly the number of non-zero rows, so that is always less than or equal to m n the minimum of the two, right. So, it is less than or equal to both the number of non-zero rows. So, the rank is always less than or equal to the minimum of number of rows and number of columns. So, and we stated the theorem of solving a system of equations in terms of this new terminology rank. So, it says the following: first of all, the solution set is non-empty, that means the system is consistent if and only if the rank of A is equal to rank of the augmented matrix. The two ranks are same, that means the pivot, it should not happen that there is no pivot in a row in A, but there is a pivot in the augmented matrix, right. So, that will give you an inconsistent equation 0 equal to a non-zero thing. So, existence is if and only if the rank of A is same as the rank of augmented matrix, that means the number of non-zero rows in A and the number of non-zero rows in augmented matrix should be same, okay, once you have them in the row echelon form. So, one is a unique solution possible, n is the number of variables, m is some m cross n is the number of variables. So, if there are n pivots exactly, right, that means each variable will get a unique value. So, the system has unique solution if and only if the rank of A is equal to rank of A plus, that is a consistency, and both are equal to n, the number of variables. Then there is a unique solution, and non-unique means actually there are infinite number of solutions when the rank of A is equal to rank of the augmented matrix. Once again consistency going on, but it is strictly less than the number of variables. The number of pivots is strictly less than the number of variables. Okay. So, then it says there are infinite number of solutions, and we said that the difference n minus r, the rank, right, those many variables will get infinite values, they are arbitrary, yeah, they are free to give any values, right. So, you can choose the remaining. So, that describes all solutions also. If the rank is equal to rank of A plus, either there will be unique solution if it is equal to n, if it is less than n, there are infinite solutions, and all those infinite solutions can be obtained by backward substitution, right, putting the non-pivotal variables arbitrary values and calculating the pivotal variables in terms of those arbitrary values, right. So, let us write a so the I think proof we have already gone through existence, and so let us skip the proof, right. Uniqueness also we have gone through, so let us. So, I am just summarizing now. If the rank of A is r, rank of A plus is r plus 1, that is one more column is there in the augmented matrix. So, the possibility is rank of A is equal to r, but rank of the augmented matrix is r plus 1, then there is no solution, it is an inconsistent solution. The solution set right. The set of all solutions is an empty set. If both are R and R is strictly less than n, the number of variables, then there are infinitely many solutions possible, right. And if both are equal to n, the rank of A is same as rank of augmented matrix is equal to n, then the solution set will be a single point. That means there is a unique solution, right. This cannot happen, R cannot be strictly bigger than n, right. Okay. The rank of the matrix cannot be bigger than number of rows or number of columns. So, this possibility does not arise. So, these are the only three possibilities which can arise. And as a consequence of this, here is some simple application which we have already discussed. A square matrix n cross n is invertible if and only if Ax is equal to 0 has only trivial solution, right. There should not be any non trivial solution for this. Is it clear? Because Ax is equal to 0, 0 is always a solution, right. And if A is invertible, that means only one solution possible. So, 0 should be the only one. Is it clear to everybody? Ax is equal to 0 always has 0 as the solution. If you put x is equal to 0, that is the solution, right. And when invertible, that means there is only one solution possible, right. Invertible means that was also equal to the row equivalent form is identity matrix, right. That was also same as saying the rank is equal to n. And we also showed that this is same as saying the product A is a product of elementary matrices, right. A is invertible if and only if it is a product of elementary matrices. We showed that, and actually that gives us also a way of computing the inverse in case it is invertible. So, all these are equivalent ways of saying that matrix is invertible, Ax is equal to 0 has only trivial solution possible, there is only one solution possible, right. You can also look at this way, if you multiply in this equation both sides by A inverse, what do you get? A inverse A x is equal to 0, that means x is equal to 0, that means the only solution possible is x is equal to 0, right. The row equivalent form should be identity matrix, right. Invertibility is same as saying that rank is equal to n, number of non-zero rows must be same as the number of variables, and that is same as the row the number of rows or number of columns is a square matrix, and product of element. So, there are various ways of saying when a matrix is invertible, right. All are same, but there are different ways of saying the same thing. Okay. So, let us look at the previous one said that the system Ax is equal to 0 seems to be a important case to consider. So, such a system is called a homogeneous system. It is a system of linear equations where the right hand side that vector b is 0 is called a homogeneous system, right. So, given a we want to relate it with the, so given any linear system Ax is equal to b, if you put b equal to 0, you will get a homogeneous system, right. So, given a system of linear equations Ax is equal to b, if you put b equal to 0, that is called the homogeneous system associated with the given system of linear equations, right, by putting. So, what is the advantage of doing that and what is the use of it? So, let us the observation is the solutions of the general system are related with the solutions of the corresponding homogeneous system. In what way? We will describe that. So, first of all, let us note that the homogeneous system always has a solution, right. Ax is equal to 0. So, 0 is always a solution of that. Okay. So, let us define all solution of the homogeneous system as a set. So, let us call that as null space. Given a matrix A, you are given a matrix M cross n. So, look at all possible x, the vectors x. So, I want to look at Ax is equal to 0. So, what will be the order of the vector x? Ax, you have to multiply A with x, A is M cross n. So, vector x has to be n cross 1, right. So, you are looking at all vectors x in Rn, say that Ax is equal to 0. So, look at that set. So, collection of all vectors which are killed by A, you can think it that way. that is called the null space of the matrix A, right, and that is same as the solution space of the homogeneous system A x is equal to 0, right. In terms of set theory, we call it as null space denoted by n of A, right. That is a solution space of the homogeneous system A x is equal to 0 for a given matrix A. So, for every matrix we are associating a space with it, a set with it, the null space, which is a solution set of the homogeneous system. Okay. What is the advantage of that? So, the advantage is, look at, we want to solve the system A x is equal to b, right. The theorem says that the solution set of A x is equal to b is same as you find at least one solution of the system A x is equal to b and add to it all solutions of the homogeneous system, you get all solutions of the system. So, finding a solution for the non homogeneous case or the general system is find at least one, find all solutions of the homogeneous case, take one from there and add it to it, you will get all, one by one pick and add, right. So, the solution of the solution space of A x is equal to b is same as x 0 plus x, where x is in the null space, that means A x is equal to 0. And what is x 0? Some particular solution, if you are able to find at least one solution of the system A x is equal to b, add to it a solution of the homogeneous system, you get a solution of the general system, right. So, what it says is that the solution of the homogeneous system is important thing to consider. Using that we can describe all solutions of the system A x is equal to b, provided we can find the null space, the solution space of the homogeneous system plus one particular solution, right. So, we will concentrate on this. So, questions are how to list all solutions of a homogeneous system. So, the problem, we are reducing the problem to the homogeneous case in a sense, and what is the best economical way of telling what are all the solutions. You can say this is a solution set, but can I give a method of generating all the solutions of the homogeneous system, right. What is the most economical way? So, let us observe something, that if x 1 x 2 are solutions of the homogeneous system A x is equal to 0, then alpha x 1 plus beta x 2 also is a solution. If x 1 and x 2 are solutions of the homogeneous system, that means A x 1 is equal to 0, A x 2 also is equal to 0, then the claim is alpha x 1 plus beta x 2, where alpha and beta are any scalars, is also a solution of the homogeneous system, because if I multiply by A, then what is the product? A multiplied by alpha x 1 plus beta x 2, that is same as alpha times A x 1 plus beta times A x 2 by the distributive property of multiplication of matrices, right. But A x 1 is 0, A x 2 is 0, so A applied to alpha x 1 plus beta x 2 is also equal to 0. So, it says that this null space, right, the solution of the homogeneous system has a nice property, that if I take two elements in it and take a combination alpha x 1 plus beta x 2 of that, that again also is a solution of it, right. So, this property we want to make it as a definition. So, let us make it a definition, a general definition now, for which particular case N A will have that property. We say that a subset V of R n, right, is called a vector space if it has that property. That is, that take any two elements in V, take two any scalars A and B, and take the linear combination A V plus B W, right, multiply V with A, multiply B W with B, take the sum, that is called a linear combination, that also should belong to V, right. So, if the set V has this property, then we say it is a vector space. So, in our example, for any matrix A, the null space is a vector space, because it had that property, right. That is what motivated us to define. So, let us look at examples. for any m cross n matrix, look at the null space. Null space is a subset of what? Rm or Rn. Matrix is m cross n, you are going to do Ax. So, x should be of the same order as n. So, null space is a subset of Rn and it is a vector space, right. Let us look at one more example. Look at A times, this is a notation A Rn. So, what is it? Look at A times x, the multiplication, where x varies over all of Rn. A is a matrix, multiply any vector x with it, you will get a new vector. So, take the collection of all such vectors, okay. That is called the image space of the matrix, or also called the range of the matrix A. That again is a vector space. Is that a vector space? For example, let us look at Ax1 is one element of this set, Ax2 is another element. So, let us look at alpha times Ax1 plus beta times Ax2. We want to show it is also in Arn, but what is alpha times Ax1 plus beta times Ax2? By distributive property again other way around, it is A applied to alpha x1 plus beta x2. So, it is A of some other vector, but that vector is again in Rn, right. It is clear to everybody. If I take two vectors of this type Ax1 and Ax2 and take alpha times Ax1 plus beta times Ax2, right, then this addition, what is this equal to? This is equal to A applied to alpha x1 plus beta x2. So, it is applied A applied to some other vector, A multiplied with some other vector in Rn. So, that is again inside this set, it is of the type same type again, A applied to something, right. So, this also is a subspace of Rn, but this is subspace of what? Is it of Rn or Rm? Your A applied to something, A is m cross n, x is n cross 1, when you apply you will get a vector of m cross 1 multiplication. So, it is a subset of Rm. So, this is a subspace of Rm. The null space is a subset of Rn, but the range is a subset of Rm. We will describe later the matrix as a kind of a map. It takes vectors from Rn to vectors in Rm, right, which are killed, there is in the domain, range is, right, where they go, right. So, Rn to Rm. So, we will come to that when we describe linear transformations, right. So, at present just keep in mind, because of matrix multiplication, the range is a subset of Rm and the null is a subset of Rn, right. They have different subspaces of different Rn or Rm. So, let us look at one more example. Consider this at L, which is alpha x, okay. There is a typo here, it should be r to the power 2. I take a, okay, I take some vector, okay, a vector in x2 r2, take some fixed vector, okay. So, let us take a vector x0 in r2 is a fixed vector, okay. Consider the set of alpha x0 where alpha is a vector in R, okay. I have a fixed vector x0 and I multiply it with different scalars. So, question is call it as L, is L a vector space? You want to know whether it is a vector space or not. So, how do I check it? Take two elements. So, let us call it y1 is equal to alpha 1 x0 and y2 equal to alpha 2 x0, both belong to L, right. Take two vectors, then what is say alpha y1 plus beta y2, what is that equal to? Oh, sorry, this is x0. So, what is alpha y1 beta y2? So, that is alpha alpha 1 x 0 plus alpha alpha 0 alpha 2 of x 0, right. Is it okay? So, what is that equal to? Alpha alpha 1 plus alpha alpha 2 of x 0. Oh, there I should have written beta somewhere. There is beta here, that is beta here, right. I take two elements in that set L, y 1 and y 2, two vectors, take alpha times y 1 plus beta times y 2. So, that gives me, so this is equal to some lambda times x 0. What is lambda? That is alpha x 1 plus beta alpha 2. That means, a linear combination of y 1 and y 2 is again belonging to L, right. Is that okay for everybody? So, this L is a vector space, yes, this is a vector space. Can you tell me geometrically what does it look, what is this vector space in R 2? We can visualize geometrically what is R 2. R 2 is the plane, right. So, R 2 is the plane. So, visualizing, so what is L? So, that is equal to alpha x 0, alpha belonging to R. Let us try to draw a picture of it. So, what is the picture? X 0 is a vector, right. So, I can draw that vector. Okay. Let us draw it from here. So, this is a vector, okay. So, that is my vector x 0. What is alpha x 0? What I am doing? I am taking a fixed vector and only stretching it, right. So, when I stretch it, its length will change only, right. So, this will give me, right, the vector could be anywhere here, from here to here or here to here or here to, depending on whether it is positive or negative. So, what is this? This is a line through the origin, right, in R 2. Is that okay, right. So, this is a line through the origin, that is a vector space, okay.